Hello everyone, I am Siddhartha. I am a PhD student at Indian Institute of Science, Bangalore. Today I will present on clustering with simplicial complexes. This is a joint work with my PhD advisor Sandeep Prabhakar Chepuri from Indian Institute of Science, Bangalore and Pierre Brognet from ENS Lyon, France. We start with a bipartitioning problem where we are given a graph with set of nodes and edges connecting this set of nodes. And bipartitioning problem aims at partitioning this graph into two sets S and S bar such that nodes within the set has high density of edges. Nodes across the set has very less density of edges. To find an optimal partition, several heuristics has been proposed. Well known among them is conductance and modularity. In particular, an edge conductance is defined as the ratio of cut to the volume, where cut with respect to set S is defined as it's a function that measures the number of edges that has one endpoint in S and other endpoint in S bar, whereas volume is a function that measures or counts the number of edges that has endpoints in either S or S bar. To find an optimal partition, we minimize the edge conductance. Often minimizing the edge conductance is NP hard due to combinatorial nature of the optimization problem. Different algorithms has been proposed relaxing the constraints and objectives. Among them, spectral clustering algorithm is well known, where it relaxes the objective function in terms of Laplacian, and it is built on Cheeger's inequality that relates the second smallest eigenvalue to the optimal conductance. Conventional clustering algorithm discussed earlier partitions the networks based on the edges that captures the pairwise relationship between the nodes, but often many real datasets has higher order structures like triangles and tetrahedrons. For instance, in a scientific collaboration network data where nodes corresponds to the author, we can find a higher order relations like triangles among the nodes due to common scientific interest among a group of three authors. Similarly, in a Karate network data, which is a social network data, nodes representing the members of a club, there always exists a higher order relation such as triangles and tetrahedrons due to the shared interest among the members of the club. With these motivation for higher order structures, we ask the following question, where we are given a network with higher order relations, how do we partition this network into two groups based on higher order structures, in particular using the fill triangles. Before discussing the method for such partitioning, now we see some preliminaries for modeling the higher order relations. Simplicial complexes model the higher order relations, and simplicial complexes has simplices as the basic building blocks. Given a finite set of vertices, V1 to Vn, a K-simplex is a subset of a vertex set with cardinality K plus 1. For instance, a node is a zero simplex since it has only one vertex. An edge is a one simplex as it has only two vertices. And a closed triangle or a filled triangle is a two simplex with three vertices. A simplicial complex is a finite collection of simplices such that for any K simplex in X, subset of the simplices must also be in simplicial complex. The relationship between the simplices of different orders are captured by the boundary operators. For instance, boundary operator Pk captures the relationship between k minus 1 and k simplex and has non-zero entries if k simplex is interested on k minus 1 simplex. For instance, for a simplicial complex of order 2 shown here, boundary matrix P1 captures the relationship between the edges and the nodes, and it has non-zero entries if edge is incident on the node. And the boundary matrix P2 captures the relationship between the edges and the triangles, and it has non-zero entries if the triangle is incident on the edges. For an unoriented simplicial complex, the boundary of boundary map will not be equal to 0. In particular, bk times bk plus 1 will not be equal to 0. With this setup, we now formally state our problem of clustering using the higher order networks. So given a simplicial complex, the two-way partitioning of the simplicial complex based on two simplices now corresponds to finding an optimal nodal partition such that zero simplices within the set has high density of two simplices and zero simplices across the set has low density of two simplices. To find such partition, we now minimize a function called simplicial conductance that is defined as the ratio of cut to volume again, where cut is now defined as a function that measures the number of two simplices that has one endpoint in S, other endpoint in S bar, whereas volume is a function that measures the number of two simplices that has endpoints in either S or S bar. Further, to optimally partition the network or the simplicial complex, we need to minimize the simplicial conductance, often minimizing or finding the optimal partition, minimizing the simplicial conductance is NP hard due to the combinatorial nature of the optimization problem. In what follows, we relax the simplicial conductance in terms of simplicial Laplacian that captures the relationship between the zero simplices through two simplices. To start with, we define the simplicial adjacency matrix that captures the relationship between the zero simplices through two simplices. The zero simplices are the nodes and the two simplices corresponds to the filled triangles. The I, jth entry of this simplicial adjacency matrix counts the number of triangles that the vertex set Vi and Vj are contained in. For instance, for a simplicial complex of order 2 with the two simplicities being 1, 3, 4 and 1, 2, 4, the vertex set V1 and V4 are part of two triangles 1, 3, 4 and 1, 2, 4. So the 1, 4 entry of A02 has value as 2. Once we have an adjacency matrix, the degree matrix is computed by summing across the rows of A02. Then the simplicial Laplacian is obtained using the degree matrix and adjacency matrix as follows, whereas normalized Laplacian is obtained using the degree matrix as follows. The simplicial adjacency matrix defined earlier can be computed using the boundary operators B1 and B2 as follows, where B12 here refers as the product of boundary matrix B1 and B2, and it has non-zero entries if vertex Vi is contained in the two simplex A. The factor 2 comes here because of the unorientedness of the simplicial complex we considered earlier. So now having the definitions of simplicial Laplacian, adjacency matrix and degree matrix, we now discuss the way of expressing the simplicial conductance in terms of a simplicial Laplacian. We then discuss the algorithm to find an optimal partitioning of the nodes of the graph with respect to two simplices. To do so, we borrow the tools from graph theory, where we first define the simplicial Jigger inequality that relates the second smallest eigenvalue of the normalized Laplacian to the optimal conductance. So proof for this simplicial Jigger inequality can be, detailed proof can be found in the paper. We just outline the key steps we used in the proof here. So recall the simplicial conductance as the ratio of cut to the value again. So assuming Zi as a function that measures the number of two simplices that has exactly I vertices in the set S, we can express the conductance using Zi as follows, where the cut, recall, the two simplex of a set is said to be cut if the set has triangles with two vertex or one vertex here, meaning that a triangle is said to be cut if it has only two vertices in S and either one vertex in S. So with this definition, we can express the cut using Zi as sum of Z2 plus Z1. And following the similar lines, we can express the volume as in terms of Z as follows. Here the factors 3 and 2 comes because of the unorientedness of the simplicial complex. So finally, the simplicial conductance can be expressed using this Zi as follows. So assuming ES as an indicator function that has 1 in ith index if the vertex VA is contained in S, we can express the cut in terms of quadratic form of Laplacian as follows. Similarly, we can express the volume of the set S in terms of quadratic form of a degree matrix as follows. With these quadratic forms, we can express the simplicial conductance as the ratio of the quadratic forms of Laplacian and degree matrix, and the constraint here avoids the trivial solution for the problem. Further, by defining a new variable as ES tilde that is defined as follows, the simplicial conductance can be equivalently expressed as follows, where if you see here, this optimization problem is similar or looks equivalent to the eigenvalue problem. So thus solving the above problem to minimize the simplicial conductance is analogous to the two-way spectrum clustering algorithm, where we have the edge cuts, and deriving the related Jigger inequality here remains the same, but the main difference being the simplicial conductance is now bounded by the second smallest eigenvalue of the normalized Laplacian, L02. So here we outline the algorithm we use for clustering of the network based on two simplices, where for input we need a simplicial complex and the boundary operators B1 and B2. Once we have B1 and B2, we first evaluate the simplicial adjacency matrix using B12 times B12 transpose by 4. But recall B12 is the product of B1 times B2. And we then find D02, which is the degree matrix. Using D02 and GH02, we evaluate the normalized simplicial Laplacian that is given as follows. Once we have the normalized simplicial Laplacian, we evaluate the eigenvector corresponding to the second smallest eigenvalue. Using the second smallest eigenvector corresponding to the second smallest eigenvalue, then we reorder the node indices with gamma k representing the the smallest entry of this normalized eigenvector. Once we have this set S, we evaluate the conductance for each k, for k varying from 1 to the size of the node set. In particular, if there are n nodes, then we evaluate this function with the k varying from 1 to n0. Then we output the set that achieves the minimum conductance. So in particular, this algorithm depicted here looks somewhat similar to the spectral clustering algorithm. But the difference being here is the normalized Laplacian and the you computed using the boundary operators. Now we discuss the results of the proposed method on synthetic and real data. For synthetic data, we consider the following simplicial complex with 8 nodes, 13 edges, and 5 triangles. Ground truth labels of this simplicial complex are generated based on the relationship they share with the neighboring nodes through two simplices. We compare the proposed algorithm across the edge-based spectral clustering algorithm, multi-spectral clustering algorithm. We see that proposed method correctly assigns the node 7 to the cluster 1, thus highlighting the importance of the higher order relations. We now discuss the proposed method on real data sets. For that, we consider the karate network data with 34 nodes and 2 classes. The ground truth labels are shown here. To construct the simplicial adjacency matrix, we first enlist all the triangles. Then out of all the triangles, we assume only some of them are filled triangles. So out of all the triangles available, just assuming the two of them that acts as the bridge between the two classes as open, we apply the proposed algorithm. Then we evaluate the NMI. We see that there is a significant improvement in performance compared to the motif clustering algorithm, where it assumes every triangle as a filled triangle. We further test our proposed algorithm on multi-class dataset. For that, we consider US poll dataset where it has 132 nodes that corresponds to books of 3 different classes. So to perform clustering on this data, we perform an algorithm similar to spectral clustering algorithm with multiple classes, where we first compute the eigenvectors of the normalized Laplacian using the simplicial adjacency. Then we use the 3 eigenvectors based on the number of classes to perform k-means to obtain the node assignments. It is clear that there is a significant improvement in clustering performance by using the higher order relation, that is in particular the filled higher order relations among the nodes of this network. So we similarly test our algorithm on another multi-class data, that is American football data, that contains 115 nodes classified into 12 groups. Here nodes corresponds to the players. To compute the node assignments, we follow the similar procedure explained earlier using the eigenvectors of the normalized Laplacian. We apply k-means on the eigenvectors of the normalized Laplacian, then compute the NMI. We can see that the proposed method achieves the highest clustering accuracy, thus highlighting the importance of higher order information while clustering. So I conclude my talk with the following remarks. So we proposed a simplicial conductance function which on minimizing outputs the clusters based on 2 simplices, and we proposed a simplicial adjacency matrix that captures the relationship between the nodes through 2 simplices, and we gave the connection of the simplicial adjacency matrix to the boundary operators. Further, we discussed a simplicial Cheeger inequality that relates the optimal conductance to the second smallest eigenvalue of the simplicial Laplacian. Further, using the simplicial Cheeger inequality, a new clustering algorithm is proposed to cluster the nodes of the simplicial complex. Thank you. Thanks for your attention.